now we get into a little bit about types of functions, and I don't want you to take this to an extreme. There's no get you gotcha here. There's nothing tricky about it. I just want to expose to you and let you understand that there's more than one type of function. Now, the type that we've been working on is the type on the left, linear functions. Linear, you can see the word at the beginning of linear is line, L-I-N-E, and we call it a line because it appears as a straight line when I graph it. And the equation of this, the general equation form, is always y equals mx plus b. The second type is a quadratic function. And a quadratic function looks like a U, a gentle turn at the bottom, it's a U. And quadratic functions can face down, as this one does, or they can face up. They're both turned quadratic. As long as it's shaped like a symmetric U, it is a quadratic function. And our general quadratic equation is y equals ax squared plus bx plus c. And last is an exponential function. And exponential functions almost look like half a parabola, generally a little wider or perhaps a little narrower, but they have this turn like you see here, okay? And a general exponential equation is y equals a times b to the x. It's on exponential that we're going to spend a lot of time in a couple of minutes. But for now, what I really want you to do is notice the differences between these equations, how the graphs look. Linear is a straight line, quadratic is a gentle U, and an exponential almost looks like half a U, but it's a gentle turn going up like that. It could be a much sharper turn. It's possible to go up at a much higher angle. But you understand those exponentials, and you understand that what the equations look like. Y equals mx plus b, y equals ax squared plus bx plus c, y equals ab to the x. There is a really key characteristic when it comes to the equations that I want you to take away here. And that key characteristic is to look at the exponents. On a linear graph, what is the exponent? It's a 1. On a quadratic graph, what's the highest exponent? It's a 2. And what is the exponent or the highest exponent on an exponential graph? It's an x. So what the highest exponent is, or any exponents, tells you the type of function it is. All right? Let's try to recognize a function by its picture. Okay? We have 3 there. One of them is a linear, one's a quadratic, one is an exponential. Label each. Go ahead. Okay, so this first graph is an exponential graph. You can see the curve coming up, but it clearly lacks the other half of what would be in a parabola. The next one is linear. It's a straight line. And the last one is quadratic because it's a gentle shaped U, and realize that you could go upside down or right side up. All right, now let's try to identify which one is which by looking at equations. Go ahead. Okay. Another few seconds. I was a little too quick there. Okay, so the first one is going to be quadratic because the highest exponent present is a 2. The second one is going to be an exponential because the variable is in the place of the exponent. That's where we find the x. And the last one is linear. Looks like y equals mx plus b, but the highest exponent on the x is a 1. Now, I've already made up quizzes, one quiz since here, and then I'll be making up a test in the next 3 or 4 days. And what I want you to realize is this. I'm not trying to trick anybody here if you get a quiz question on it, and I actually think it's going to be one of the easiest quiz questions going, as long as you take the time to remember what the graphs look like and what the equations look like in general. A question might be, hey, here's the equation y equals 1000 a to the x. Is it exponential, quadratic, linear, none of the above? So that's the kind of thing that you would be asked. Nothing overly complicated, but you do need to know what each is. Now, I wanted to go over these because there are some very real life applications for them. For instance, with linear functions, every time you go to a gas pump and put gas in your car, if you took a chart or a graph of it, you would be making a straight line. Let's just round it off in the present day economy as it stands right now. Let's go $4 a gallon for gas. 1 gallon is $4. 2 gallons is $8. 3 gallons is $12. 4 gallons is $16. 5 is $20, and so on. That's a slope of up 4 over 1, and a y-intercept of 0, because if you don't buy any gas, you start at 0. But that's clearly a linear function. So paying for gas, the output of gas, that's linear. Another one is how much miles you drive in a given course of time, assuming that you're on cruise control and your speed stays the same. I know that never happens, but let's just assume it. That would be an example of a linear function. And my dad, he was a railroad conductor and for the Long Island Railroad, and my dad would be paid for a normal 40-hour work week. And if you are paid by a normal 40-hour work week, and I assume that's how most of you are paid, then if you get, say, $15 an hour, 1 hour is 15, 2 is 30, 3 is 45, 4 is 60, and so on. That's another example of linear, okay? The slope is, or the rate of change, slope, same thing, is constant throughout. So those are 3 examples of many real-life applications of linear functions. Next up, what about quadratic functions? Well, one really cool one, in the 3 dimensions, if you can imagine it, is a headlight of a car, because it takes the light in the shape of a parabola. You can see the back end of the bulb or of the housing right here is a parabola, and it uses it in 3 dimensions to focus the signal. You know where else you see it is when you see a satellite dish. It focuses the signal onto the receiver. And you also see it like on the sidelines during football games when they have what they call parabolic mics sitting there to pick up the sound of the quarterback going, 10-21, 10-21, blue, blue, that kind of thing. Electrical circuits. Quadratics are used a lot in electrical circuits and resistances in them. And another great example is in sports. In this case, it's baseball. When a ball is hit up in the air, it goes up, it comes down. And assuming no wind, it forms a perfect parabola shape, just like the diagrams that we showed before. It's true of baseball. It's true if you're shooting a basketball, all of those things. So that's where quadratic equations and quadratic functions get involved in our real life. What about exponential functions? Real life applications in exponential functions. And this is a really common one. Starting at the top, bacteria, virus. We've just survived is a little bit of a strong word, but we've been battling this coronavirus epidemic, and I think all of us know someone who's either been very sick because of it or who has passed because of it. It's tragic, it's heartbreaking, it's terrible. And in exponential functions, what happens, you remember what that exponential curve looks like. You get to a point with the bacteria or virus in your body where there's so much of it that its population explodes and it becomes overwhelming to your body and it can't defend itself against it. Okay, cancer, same thing. So there's very much a danger to pathogens as they get into your body. Another example would be wildlife. There's a balancing point in wildlife, and whether it be wolves returning to Yellowstone, as this picture suggests, and if you don't know the story behind wolves returning to Yellowstone, I would just go to YouTube and enter wolves returning to Yellowstone. You'll see a really cool story about how it balanced everything out. But the population will follow, whether it be wolves or humans or bacteria or birds or anything else, unless there's some limiting factor set into the equation. The population growth will follow an exponential function. Or money. Money, absolutely, when you get involved with compound interest, and that's pretty much the way of the world, money is very much an exponential equation. All right, so we've introduced these to you, and then the next story I give will be a real-life experience, very, very real-life experience with money involved.